Okay, so welcome everyone to the ICT testing seminar. So today we're very happy to have Chris Akers from MIT, who will tell us about black holes as non-isometric codes. So Chris, over to you.
Thank you. Yeah, so the big overarching goal of some long-term program is that we want to understand black holes and quantum gravity. And to zoom in a little bit to the topics that we'll be discussing here, a particularly useful tool for doing this has been the quantum extremal surface formula, which says the following thing. And I'm only going to tell it to you in a special case. I think many of you will be familiar with this, but I'm not going to need the full power of the so-called quantum extremal surface formula, which involves extremizing in the time direction as well as minimizing in the space direction. I'm going to consider the case that applies whenever you have, say, a moment of time symmetry in the bulk for you who already knows what that is. Because that's the situation that we understand the best, and that's all I'll need later on. So in the special case, which is called the quantum minimal surface formula, the prescription is the following. So this is in the context of ADS CFT, at least originally. And so here is a time slice of ADS CFT, where on this blue circle here, we have a time slice of, say, a CFT, a conformal field theory. So a state would live on that circle. And then inside that circle in the disk is a state of its dual theory, which is state in the ADS, the gravitational theory. And what the quantum minimal surface formula says is that you can compute the von Neumann entropy of some boundary subregion B using some very nice prescription applied in the dual, so in the ADS theory. So you pick, say, some subregion B of the CFT, and instead of having to compute, take its density matrix rho and compute minus trace of rho log rho to get this quantity called the von Neumann entropy, you can instead use the following formula, which is in many situations much easier to compute, where you look at the bulk, so you look at its dual, and you consider all surfaces that, say, like these orange surfaces that are homologous to the boundary subregion B. So, this one's homologous, this one's homologous. And to each of those surfaces, you associate these two terms. So one is just the area of that surface, the literal geometric area of that surface in the ADS geometry, divided by 4g Newton. That's Newton's constant. And then the other term is S, so the von Neumann entropy of the bulk fields in the homology region. So for this surface, that means the von Neumann entropy of the fields, the bulk fields like the graviton and the scalar field or whatever is in the ADS theory, between that surface and the boundary subregion B. That goes here. You add those together, that gives you the so-called generalized entropy, which is some nice dimensionless number. And so you've done that for every orange surface, and then you find the one that minimizes it on this time slice. And that is called the quantum minimal surface. And then this sum for that quantum minimal surface gives you the von Neumann entropy of your boundary subregion B. And that is the so-called quantum minimal surface formula. Now, this formula has turned out to be really important. For example, it's basically involved. The QES formula has been involved in computing to the page curve in these toy models recently, and for many other reasons, say helping us understand bulk reconstruction. If you know what that is, I'm going to remind you. So because it's so important, there's been a lot of work trying to understand it, and there's going to be two key results that are going to be important as background for the rest of the talk. And these two key results are those that tell us that we can understand the quantum minimal surface formula as a feature of quantum error correction. So let me give you the precise statement for that. And the statement is made in the following context. So before I show you the precise statement, which will be labeled theorem. Let me tell you the context. So the context is very simple. You just have a linear map V. And that linear map is a map from one Hilbert space to another. And so here at the input Hilbert space, I have drawn with this tensor product decomposition. It doesn't have to have some special tensor product decomposition, but it could. So it's allowed to have some special tensor product decomposition. And then the output, we will, without loss of generality, it won't matter so much that has some big tensor product decomposition. All that matters is that it's allowed to factorize into two different factors, which we'll call capital B and capital B bar. So the linear map maps from two Hilbert spaces. The input is allowed to have some special factorization. So the cartoon picture that I'll come back to over and over looks like the following. So we have some V, and the inputs will come in from the left. So sort of time moves from left to right in these diagrams. And each line represents a Hilbert space. So this top line is B1 here, like this guy, and so on. And so you have all these Hilbert spaces, and they're tensor producted together. That's this. You act V on them, and then you get out this output Hilbert space. That's a cartoon of this linear map. For those of you who would like an ADS-CFT visualization of this, right? Because all of this connects back to ADS-CFT. It would look like the following thing. It's not super important that you imagine the linear map in this form, but it does connect to ADS-CFT, and this is how it does it. So here, the map V itself is sort of implicit, and it's a map from all these little b's, which are living where the ADS lives, it's a map from those to the boundary circle here, where the capital B and B bar factors live. And so all these little b's, you might imagine, are different, they represent different subregions. So all the degrees of freedom in different subregions of the bulk. So that the special factorization in the input is like the spatial factorization in the ADS theory. And then the boundary is we're just imagining it factorizes into B and B bar. And I know that everyone is probably familiar with the fact that in real life, the CFT is not some algebra that just can factorize. It's something much more complicated. It's a quantum field theory with type 3.1 algebras. And that's totally true. So in this sense, this theorem, as I'm stating it now, is sort of a toy model for that. So it's imagining you have a finite dimensional Hilbert space. So you might imagine that you've placed your CFT on a cutoff and maybe restricted the range of some of the fields. Or more realistically, what I might say is that this finite dimensional setting is just the simplest to prove and state for people. And historically, theorems like this are proven, and then later people like Monica Kang and Tom Faulkner come along and upgrade the finite dimensional proofs to the infinite dimensional, like type 3.1 setting. Everything goes through. And so the intuition from the finite dimensional case is correct. But I'm giving you the finite dimensional setting.
Sorry, I have a question.
Yeah.
So is the understanding that for different B1, B2, B3, etc., you would have, the map would depend on the nature of the B1, B2, B3, and the B and the B bar. The V's would depend on the nature of those.
Yes, that's right. Yeah, I mean, they would all be related, but it would be a different map in some sense. Yeah.
Yeah. Okay. Good.
Yeah, that's right. Thank you for the question. Okay, so that was the ADS-CFT analog. So now let me tell you the precise statements, these statements that connect quantum minimal surfaces to quantum error correction. This is again the background part that I want you to know before telling you the meat of the result of this talk. So the theorem, this is a theorem that I'm going to say comes from these two papers, one from Harlow in 2016 called Ri Takinagi from Quantum Error Correction, and then this one by Jeff and me last year called Quantum Minimal Surfaces from Quantum Error Correction. The theorem I'm going to state is qualitatively from both. Really, I'm going to state the one that's closer to this theorem, because this more recent paper has the is basically a more general, complete version of the theorem here. It won't really matter what the differences are. So you might as well just understand that qualitatively, it's both of these papers that gave the following theorem. So again, this picture was the context for the theorem. And the theorem says that that two statements are equivalent, essentially. It actually has more statements, but two statements are equivalent in particular. So the first statement that will be equivalent to a second statement that I'm currently hiding from you is basically that you have this quantum minimal surface formula that given such a linear map, if you want to compute, so you're supposed to imagine that you input some state psi to the input side. So like you pick some psi in the Hilbert space of all these guys. So we're calling that psi, like the logical state psi. Logical means input to some quantum code. You put that in, you act V on it, and then you get some state out on BB bar. You want to compute the von Neumann entropy of capital B in that output state. You can do it with this holographic looking entropy formula, where A of B is some interesting function that can be interpreted as area that I won't go into. I won't go into it too much. This is the von Neumann entropy of some, so little b is supposed to be some union of like the BI's. But the point is that you get some holographic entropy looking formula. That's the condition that you have that for your V is one of the two conditions that are equivalent. Not all V will have this, surely. It's a kind of strong condition, but it's an interesting one to consider because ADS-CFT codes seem to have it. That condition is equivalent to one that looks like quantum error correction. So it's to a reconstruction condition. So it's equivalent to the statement that using just B, so acting operators just on capital B, you can reconstruct operators that act on little b. So in case the way I've written it is confusing, but I mean, whatever little b up here minimizes the right-hand side, that little b shows up here, and capital B can reconstruct operators that act on that little b. In a sense that maybe you're familiar with. Later on, I'm going to be very careful with what I mean by reconstruct, but this is supposed to just remind you. And essentially it says that for all unitaries on little b, there exists a unitary on capital B such that the following thing is true. That like if you had taken your input state, the one that is like in the Hilbert space of all the little b's, and acted that unitary on it, and then acted V, so encoded it to get a state on the capital B bar system, you could have done the same thing, gotten the same state by first taking your input state, not acting this U little b yet, just encoding with capital V, and then acting that particular unitary on capital B, you would have gotten the same state. So the fact that this is true, it is also non-trivial. And in fact, this isn't true for necessarily all unitaries, just for all in some class. But that class isn't going to be super important right now. So this is also a non-trivial statement. And it turns out that these two non-trivial statements are equivalent to each other.
Sorry, what does U small b do on psi? Because psi is just constructed out of the b's, as you have said in your previous slide.
Yeah. So psi, right, exactly. As you said, so psi is some state that's input into here.
Yeah.
And I'm imagining that U little b is some U with non-trivial support on some of these BIs, these little BIs. And so, it acts non-trivial in psi. So this will give you some state, like, so U little b can change psi to something else like phi, then you encode it with V. That gives you some state. And the non-trivial claim here is that you could have gotten the same state if you had just first taken psi, not acted anything on it, just acted V immediately, and then acted some unitary only on this factor of the output.
Okay, good.
Yeah. Thanks for the question. Okay, so this is important for ADS-CFT, right? Because the QMS formula works in ADS-CFT. You know, we have some arguments for it from the Euclidean path integral. And so these theorems suggest a sharp sense in which we can think of the ADS Hilbert space as like the logical Hilbert space, right? The input to some code. And the CFT Hilbert space is the physical. Right? In this sense, this theorem offers perhaps the sharpest sense in which we can say, yeah, this is the evidence that ADS-CFT is quantum error correcting code. And
in the from the code way of looking at it, what plays the role of G Newton?
Good, yeah. So for general code, it's not obvious. So this area function here is a particular defined thing, and so you would expect like 1 over G Newton would show up there. So from in that language, it's like a certain entanglement in the physical Hilbert space. So like this area will increase whenever there's a lot of entanglement between B and B bar that isn't there from like entanglement between the little b's, if that makes sense. That's sort of kind of what you expect from the Ryutaki-Yanagi formula, where the entanglement of some boundary subregion is given at leading order by this area over 4G Newton, even though that area over 4G Newton is not part of the von Neumann entropy of any bulk subregions. It's part of the generalized entropy, but not the von Neumann entropy. To give you maybe a more direct answer, it's a little subtle, but there for these general codes. For more specific V's, like a tensor network, so a special case of this setup is if you have if V can be decomposed into, say, a tensor network, then it's clear how to say what G Newton is. It's, say, like the bond dimension of, or the inverse bond dimension of the tensors.
Thank you.
Yeah. What's being minimized in the expression below the picture?
Here, oops. Yeah, so you're minimizing, good, yeah, you're minimizing over choice of B, where all those choices are the combinations of these different BI.
So you're imagining partitioning the bulk in a similar way to the way the boundary is partitioned? I mean, I assume you're having in the back of your head some notion of bulk locality where you picture some analog of the bulk Ryutaki-Yanagi service, which separates the B's into 2 pieces, and you're somehow minimizing over that partition. Is that the flavor of what's going on?
That's exactly right. That's exactly right. So in these codes, you are allowed to have some special tensor product structure given to you, and that special tensor product structure has the interpretation of the spatial tensor product structure in ADS. And the point is, yeah, you're minimizing over. So yeah, the surface is defined by the stuff it includes, like the region of the bulk it includes. So yeah, so up here, I guess whenever I first introduced this, I was minimizing over gamma. I might have equivalently said minimize over the region B that is a homology region for capital B and some surface. And that's the version that I'm writing down here. I hope that makes sense.
Okay.
Yeah. Thank you for the question. So yeah, so saying, like, having such a theorem and saying this is a sense in which we can think of ADS-CFT as a quantum error correcting code is more than just giving us words or a nice way to think about ADS-CFT. It actually helps us resolve some conceptual puzzles that we had, such as the so-called radial commutativity puzzle, if you're familiar with that. So taking this idea where there's quantum extremal surfaces, there's quantum error correction, has been a fruitful one an ADS-CFT when applied there. And so the point of this talk is really to take that lesson and now apply it to black holes to learn about them. And so that's what we're going to do. And it's going to be a little more subtle in some ways. And the primary subtlety will be that the code that describes an old black hole will have to be non-isometric. So this V, instead of being an isometry, like it was often assumed in ADS-CFT, it'll have to be a non-isometry in certain cases. And this is going to have significant implications, which I'll discuss. So let me give you the background to get there. So recall that we have two distinct descriptions of an evaporating black hole. One is the semiclassical description, which I might draw in this diagram. So here I've drawn basically a Schwarzschild semiclassical black hole, where this is a Penrose diagram. This blue dashed line is the event horizon, and this orange shaded region is, say, the collapsing star that formed the black hole. And these orange squiggly arrows are, say, photons, like Hawking quanta. So the ones on the outside are, say, the exterior radiation carrying energy away from the black hole. And the ones on the inside are their interior partners. And these orange dashed lines that connect them represent entanglement between them. So this is how, say, Hawking might have imagined an evaporating black hole. Okay, and then there's also this second description that is sometimes invoked that I will call the manifestly unitary description. And it might be drawn the following way, where it looks like it's the same drawing, except I've cut out the region behind the event horizon. I've cut out this whole region, and I've replaced it with something, let's say, just outside the event horizon, maybe like a few Planck lengths, and replace that with something that I've called the stretched horizon. That's the name that's often given. And the stretched horizon should be thought of as just a quantum object that has a number of degrees of freedom proportional to the area of the event horizon, or the area of the stretched horizon, because those things are very close.
I have a question.
Yes.
So when you say, can you just lower the slide?
Yeah.
So when you say that the event horizon is represented by the diagonal line, and the diagonal line coincides with the singularity at the right end, does that mean, there. So does that mean that the event horizon is shrinking from, say, the initial finite portion or finite length to some zero length at the end of the evaporation? Is that the...
Yeah. So there is some subtlety. Yeah, essentially, yes. I haven't really drawn the typical cartoon picture for a black hole that undergoes complete evaporation and then you end up with flat space again. But that is essentially what you said, is essentially the picture that I want to draw.
Yeah, but then I'm also confused by the fact that it also sort of seems to coincide with one end of Scri plus. So, but Scri plus is supposed to be at, I don't know, is it at t equals infinity, r equals infinity, some sort of thing?
Okay, yeah, good. Yeah, so the picture that I've drawn is a typical black hole, and like the Schwarzschild black hole and the complete semiclassical limit where it doesn't evaporate at all, and then the event horizon is sort of always there. If I really wanted to draw the typical cartoon picture that might be more satisfying for you, I guess there's a lot of different ways of drawing this cartoon picture, but it might look like something like this, where the event horizon ends sort of at this point, but it doesn't touch Scri plus, and it just this line right here, this vertical line, is like r equals 0 again. That's one way of drawing this cartoon evaporating picture. Like if it evaporates, the event horizon won't reach out to Scri plus.
Okay.
Yeah. Thank you. Good. Yeah. And so just going back to this manifestly unitary picture. So you're supposed to imagine here that all the degrees of freedom on the inside to have an analog state on the stretched horizon, roughly speaking. So in the sense that the exterior quanta were entangled with the interior quanta, in this picture, there's no interior quanta. They're instead just entangled with each other and with the stretched horizon. That's the way the picture is usually understood. And I'll say more about this picture as we go. But there's these two descriptions that people invoke, and there's reasons that people like each of them, but they seem to give different answers for different questions. For example, the entropy of the radiation. Right. So, and let me emphasize in this manifestly unitary description, this is one that might be valid to someone who, say, always remains outside of the black hole. And because if you were to say use the perspective that you could just replace the black hole with, and not think of it as some region of space-time, but instead think of it as some quantum object with its own Hilbert space of certain dimension, that would be like taking this perspective, and then from that perspective, of course, when it radiates, the information comes back out, and this radiation should contain the information of what went in. These are the words that are often said around this picture. So when you say that, you arrive at this different idea of what information should be carried out by the radiation. So let me say that precisely. So in the semiclassical description, the plot of the radiation as a function of time was expected. This is what Hawking would have originally said would be the correct plot. So right when the black hole forms, so we're going to compute the entropy of the exterior radiation, so like these guys out here, as a function of time. And so at time t equals 0, right when the black hole is formed, there's no exterior radiation, and so its entropy is 0. But as more and more radiation comes out, the entropy keeps going up and up and up. And eventually, that just happens forever as long as the black hole is still around. It keeps radiating and the entropy keeps going up. Eventually, the black hole finishes radiating because it has disappeared. And so the entropy plateaus at whatever it ended up at. That's what you would imagine from this picture, where the exterior guys are just always entangled with the interior guys, arguably. Okay, and then from the manifestly unitary description, the expectation has been a different curve, and there might be a disagreement about, particularly in this crowd, about exactly what you have to do to get this plot here on the right hand side. But I'm happy to happy to say more words about that if people want. But I would say a common expectation for this picture is that at early times it will follow the same path, but around halfway, which is called the page time. So the page time, more precisely, is when the coarse-grained entropy of the exterior radiation equals the area over 4G of the remaining black hole. At that time, there's a phase transition, and it no longer matches this naive answer. Instead, the all remaining Hawking quanta that come out actually purify the earlier radiation, or decrease its entropy. And so the entropy will decrease as a function of time from then on, until the black hole is completely radiated away, and then it'll plateau out at whatever the initial entropy of the star was to form to collapse it. And this more non-trivial curve is called the page curve. Okay, so famously in 2019, a surprising connection between these descriptions was found, as you'll likely recall, and that in the language that I want to use, that connection was that one can compute the page curve, which is the entropy in the manifestly unitary description, using the QES formula applied in the semiclassical description. So to write it in an equation, you can compute the manifestly unitary answer. So that the one following this curve, with this formula, which we recognize as the QMS or QES formula. And I'm actually going to call this a use of the QMS formula because there exists a time slice in which the quantum extremal surface is the quantum minimal surface. So if that didn't bother you, don't worry about it. But yeah, there's these results called the quantum maximum results, where you can specialize your quantum extremal surface calculation to a certain time slice, and then it looks like quantum minimal surface calculation. And the only reason I'm doing that is that I want to make a connection to the theorem we had earlier, which is technically only about quantum minimal surfaces, the simpler case, because we don't fully understand the quantum extremal surfaces. But that's just motivation. So these are the words I would say to help us apply that as motivation to this real world case. And so recall that we learned to understand the QMS formula as a feature of quantum codes, in which this formula held. So right, this was just the quantum minimal surface formula that we had in that theorem. And so what I want from you is to just look at these two formulas and say, perhaps this is telling us that we should think of the manifestly unitary description as the physical description of some quantum code, and the semiclassical description as the logical or input part of some code. That's the motivation. That's right. So so the theorem said where there's quantum minimal surfaces, there's quantum error correction, and vice versa. And so now we're just noticing that in these page curve calculations, there was a quantum extremal surface formula. And so now we're saying, perhaps we should understand there being quantum error correction here. And there should be, one side should be the physical Hilbert space and one side should be the logical Hilbert space. So to really write that out in pictures.
But how are you going to encode the radiation in terms of the BIs? Because I would assume that the BIs were certain bulk regions, demarcation to some certain bulk regions, right? But the radiation. Okay. Yeah. Go ahead.
Yeah. I'll say this all, I think, in a satisfying way momentarily. But yeah, I'm gonna have all the radiation and the interior be the input, and then a different picture of the radiation and the stretched horizon be the output. I'll say this all very shortly.
Okay.
So so just to drive it home, so I'm imagining, so this suggests that maybe there's some quantum code V in which the semiclassical description is like the input description, and then the manifestly unitary description is the output description. So in other words, this suggests that the logical Hilbert space is all of the interior and exterior qubits. And so like in the semiclassical picture, I might draw this time slice, this green time slice, and then all the degrees of freedom on that time slice, I want to say are the degrees of freedom in some logical picture, the logical Hilbert space, and their logical state. So the input state is their semiclassical state. And then I want to say that the physical Hilbert space is all of the stretched horizon qubits and the exterior qubits. So it's everything on, say, this time slice, which includes the outside guys and the stretched horizon. Okay. And now here's the subtle part. After the page time, the semiclassical description actually has more degrees of freedom than the manifestly unitary description. So the semiclassical description and the manifestly unitary description, they both have in Hawking quanta outside the black hole, right? That part doesn't change. All we've done is replaced our representation of the black hole. And after the page time, so the manifestly unitary description, it always has roughly A over 4G stretched horizon qubits up to some order 1 factor. Has this many qubits describing the black hole. But in the semiclassical description, after the page time, by definition, you can have more. You need, say, S interior qubits, which is greater than A over 4G. So that's weird, because that means the quantum code can't be an isometry, because recall, an isometry is a linear map that preserves inner products. So if V is an isometry, that's equivalent to saying that for all states, say phi and psi, if you stuck v dagger v in their inner product, that wouldn't change it. So v dagger v is the identity in that Hilbert space.
Hi, I have
Yeah.
that. So before page time, someone who's going to fall in would know what would he see inside before reaching the horizon. Is that a right understanding?
Yeah, so I would say before and after, yeah, perhaps you can still trust the semi-classical physics. I don't want to make, I'm not making a claim about the, before and after, can you trust the semi-classical physics or not? I would say in both cases, before and after, you perhaps still can. Yeah, the difference is that the way that the two descriptions, the semi-classical or logical description in this code, and the manifestly unitary or physical, the way that those are related changes in a qualitative way afterwards versus before. Maybe I'll make that clearer. Yeah.
I have a question.
Yeah.
In general, the understanding is that when a black hole radiates, the outgoing radiation is entangled with the interior of the black hole, right?
Yeah, that's the semi-classical description here. Yeah.
Yeah. So how is that playing out here?
Yeah, good. So what you described is what I'm calling the semi-classical description here. And so what I'm calling the exterior qubits is I'm saying that there's, say, n of them. And then there's a bunch of interior guys, which include their interior partners, and then also the degrees of freedom of the star that form to collapse the black hole, that collapse to form the black hole. And all of those together I'm calling S. And so yeah, there are the partners, and I'm counting all of them. And I'm counting all of them because, you know, they're all degrees of freedom in their own right. I could fall into a black hole and measure them at different points in the black hole's life, for example.
And the understanding, I guess, is that the outside, when you measure radiation, you get the von Neumann entropy by, say, if you consider that the regions are outside and inside the black hole, A and B, and you compute the von Neumann entropy of the region outside the black hole by tracing over the interior degrees of freedom, right? Is that correct? Isn't that correct?
Yes, right. I mean, you would get the semi-classical answer here if you, the semi-class, right. In the semi-classical description, it looks like these are completely different tensor factors. What I'm calling the semi-classical description, they're different tensor factors, which, you know, we know not to be true in the full physical description. That's more like this manifestly unitary description I'm talking about.
And what happens in the manifestly unitary description?
Yeah, in the manifestly unitary description, we are more careful. This is something that seems more in line with what we believe of quantum gravity, where the radiation outside follows the page curve or purifies as a function of time. In this way of talking about the manifestly unitary description, there is no interior at all. It's the black hole has been replaced by the stretched horizon.
But then how would you compute the von Neumann entropy by how do you compute the entropy of the radiation?
Yeah, good. So in this here, like the radiation would have a state rho, and then the von Neumann entropy of the radiation, it would be correctly computed at all times by minus trace of rho log rho. Up here, that would not be the case. There's some other state, rho semi-classical, and S rad would not, in general, after the page time, be equal to rho semi-classical log rho semi-classical. Right, because this would give you the thermal answer at all times, which is not the answer that we believe. But down here, it is.
But how are you assured that they would match? Because
how am I sure that Yeah, so this answer won't match this answer.
But
Was
they
that
have
part of
to,
your-
right? Because they are the same things.
No. So yeah, they're not just two different equivalent descriptions. They're two different ways we might describe a black hole evaporating. But the physics here, we expect to require non-perturbative corrections that become important after the page time. And the way, right, so the way that you would get the right answers here, right, that's been like the study that we've done over the last few years. There's many ways of talking about how you might fix up this upper picture to get the correct answer. You know, some people add in these, you talk about these wormholes, these replica wormholes, or you might invoke the fact that, okay, you really can't tensor factorize the input, the interior and the exterior. So you can't honestly, after the page time, compute the entropy outside, etc. All of those subtleties, though, are not present in what I'm calling the semiclassical description. This is the semiclassical description as Stephen Hawking would have written it down originally. What that gives the wrong answer after the page time. And that what's right. So what was important was that even though this is naively giving you the wrong answer for the entropy of these guys outside, it is still useful. Like it still has this connection to the second description, whose radiation does follow the page curve, through the QES formula, where you can compute the entropy of these guys using the QES formula in this picture. That was the connection that I needed between them.
Yeah, the QES formula is the bulk computation of the entropy, but there should also be a computation from the point of view of the radiation, right? I mean, the boundary computation.
Yeah, the boundary computation is to take the state of these guys and then just plug it into minus trace of rho log rho, the standard formula.
And that matches the QES formula?
Yes, exactly. That matches the QES formula. That's the content of these theorems. Yeah, that you get the right answer for the entropy. Okay, so it matches here. I mean, that's what this picture. In this picture, the radiation really is following the page curve, and so, of course, you're going to get the page curve by using this formula. The surprise, so that part is not, that was put into this picture by hand. So the surprising part was that you can have a connection between this picture, where you get the page curve from this formula, and this picture, where you don't, with the QES formula.
Sorry, say that again.
Yeah, the surprising part was not that this one has the page
perhaps
curve.
we can have this discussion after the talk, because I think this is not really the subject of the talk, right?
Yeah.
If that's fine for you.
It's good for me. I would be happy to have this conversation continue afterwards. Thank you.
Okay.
Okay, so yeah, remind me. Okay, so the point was that I claim that right, the semiclassical is the logical, and then the manifestly unitary is the physical description. The encoding map from semiclassical to unitary can't be an isometry, because you can't define an isometry from a larger Hilbert space to a smaller one. So the quantum code embedding the semiclassical description into the manifestly unitary one can't preserve inner products, because it can't be an isometry. And that's very surprising or heretical from the point of view of conventional quantum error correction. Let me say as an aside that the theorem we started out with that said you get quantum minimal surfaces whenever you have quantum error correction, that still holds, even though this conventional, even though it's not an isometry. Actually, that theorem didn't rely on it being an isometry. It was somehow more general. But anyways, it is very strange from the point of view of quantum error correction, as quantum information theorists have usually considered it. So here are two reasons why non-isometric codes haven't been considered by quantum information theorists before, to my knowledge. So there's a theoretical reason, which is that historically quantum error correcting codes were designed to protect all of the information of the logical qubits, and only an isometry can do that. Right? If you throw away some information about which states are orthogonal, then you've thrown away some information. And more to the point, you can't encode all of the information of n qubits into a smaller number m qubits. And that's actually a theorem, and it's a theorem that kind of just makes sense. Otherwise, by recursion, you could encode an infinite number into a finite number. But there's also a practical reason why non-isometric quantum error-correcting codes haven't really been considered. And the practical reason is it's clear how to implement an isometry efficiently. So here's an example. So let's say we have some isometry V. It takes as input, say 2 qubits, and outputs a state on 4 qubits. That could be an isometry because it's mapping a smaller to a larger Hilbert space. And you can, in general, do this. You can implement an isometry in the following way. You just start with your 2 qubits, bring next to it say, like, let's say 2 additional ancilla qubits that are in some initialized state 0. And then you act some unitary on them, on all 4 of those qubits. And then you get out some state on your output qubits. This is in general possible to implement in a lab because you can always add in some extra qubits and you can always act unitaries. And a general isometry can be written this way. However, a non-isometry is not generally easy to implement. Here's one way you might try and do it. So a large class of non-isometries can be done this way without loss of generality, and you'll see it's hard. So let's imagine that this is just some arbitrary non-isometry. So we have 4 qubits, so they could take some state, and we want to map those 4 qubits to a state on 2 qubits. One way you might do this is sort of the flipped version of this circuit, where you just take your 4 qubits, you act some unitary on them, and then you post-select 2 of them onto the state 0, which means mathematically you act like bra 0 on them, maybe up to some rescaling. Or, yeah, but in real life, you can't just choose to act bra 0. What you can do is you can measure those qubits, but measuring has a random outcome. It's not, in general, going to give you exactly what you want. So you can measure it and hope that you get the all 0 state. If you do, then you can say that you have successfully implemented the non-isometry that you wanted to. But if you don't, then you failed. And you can try again, initialize your qubits over here again, act U again, and then measure again, and hope you get 0. And then you can try this over and over and over until you do successfully measure 0. But that will take, in general, an exponential number of trials, because measuring what you want, the probability goes down exponentially as the Hilbert space dimension of the things you're measuring grows. So that is an inefficient way of trying to perform any particular map. So in general, it's hard to implement a non-isometry. There's a theoretical reason and a practical reason that non-isometric codes haven't really been considered before, but neither of these reasons concern us.
Can I ask a question?
Yeah.
So couldn't you, I mean, if you just took this operator U here to be the inverse of the operator that you used in implementing the isometry?
Yeah, this guy.
Right. If you just took the inverse of this operator, wouldn't that do the job?
Good. So yeah, so that will work anytime that the input here lies in the image of the image of states like this.
Oh, okay, right, okay.
Yeah, but not all states out here will. I mean, not all states that you can put in here will lie in that image. So thank you. Yeah.
So in general, what is it that tells you that there is a non-isometry? Because I would suppose that capital B would in general not be a simple, I mean, it would not be constituted necessarily of qubits that are less than those constituted in the small b's. Isn't that correct? Why is it necessary that capital B would be constituted of qubits that are less than those constituted in B?
Right. So yeah, the reason I started talking about non-isometric codes was basically this argument here, that in this particular case of an evaporating black hole after the page time, I claim that you can conclude there should be fewer degrees of freedom in the manifestly unitary description. or the capital B than there were in the input systems. That was the reason. So in most codes, that's not the case, right? In most codes, so it's as you said, where the capital B has more degrees of freedom.
But this is a natural thing, right? I mean, if you consider the physical system and the manifestly unitary systems, it is natural that they would have different sort of number of qubits, because the physical system has both the interior of the black hole as well as the exterior, whereas a manifestly unitary system has just the exterior.
Exactly.
So I mean, I don't see why one should kind of. I mean, it's not an unnatural situation. That's what I'm saying. I mean,
well, yeah. So you agree with me, yeah. So it's not unnatural from the point of view of gravity, but it's just from the point of view of codes, quantum error correcting codes. That is an unusual thing that people haven't spent much time thinking about. That was the point, and we want to bring in quantum error correction because it seems like the quantum extremal surface formula applies in this gravitational setting, and we have these theorems that say where there's the quantum extremal surface formula, there's quantum error correction.
Okay.
Thank you. Oops, sorry. Okay, so basically, we don't have these two concerns. So we just care whether or not the code describes gravity, not whether it's easy to implement in a lab. And we don't have the same theoretical concern because it's actually a feature and not a bug that not all the information is encoded in the physical state. And this last point is kind of subtle. So let me try and explain it. I might not, I'm happy to explain it more also during the question session, but let me give the gist of what I mean. So there is evidence that gravity, semiclassical gravity sort of works this way. We don't trust everything the semiclassical description tells us. Like some information is not physical, right? So if I give you the semiclassical state, you won't trust that all of your possibly very complicated measurements on the exterior radiation are going to give you answers consistent with the semiclassical state, right? So like the semiclassical state, you plug that into formulas, like, and you computed. So let me go here. So for example, if you took the semiclassical state and you tried to, and you wrote down, if you thought that was the correct description of an evaporating black hole, you might say, let me perform some measurement whose expectation values are described by some quantity like this. You would think that where rho rad is the density matrix in the semiclassical description, and then O is some operator. There are certain operators, say complicated operators, where if you plug them into this formula, they would give you some answer consistent with like the thermal expectation value of that operator, because in the semiclassical description, this radiation is just thermal. And that would not actually be the thing that you measured, right? Because the thing that you measured would be consistent with this radiation whose state is actually purifying. I apologize if that was too fast. I would like to get to the next thing, and I'm happy to talk about this. But I'm not saying anything that I think that you'll disagree with. I'm just saying, in the semiclassical description, that we believe is not correct because has all these erroneous assumptions like the inside and the outside factorized. There are some observables that disagree, like that you wouldn't measure in agreement with your expected computed answer if you used the semiclassical state. Okay.
In the manifestly unitary description, what are you assuming about the interior?
So maybe we can let Chris go on and then leave this discussion for the end.
I appreciate your questions. Yeah. So in the manifestly unitary description, I'm really just replacing the interior with the stretched horizon, which has its own state that is a little bit more mysterious. I'm not prescribing any particular Hamiltonian to it. I'm being agnostic about that. And so the philosophy here for why we don't trust the semiclassical description for all observables is in this code language that there are some operators that are not reconstructible into the physical picture. So there exists some O's here such that there's no O tilde such that these two expectation values would give you the same thing. The point of that was just to say that this suggests that the code relating the semiclassical and the manifestly unitary descriptions it's a non-isometric code in which the reconstructible set of operators are those we trust to be physically meaningful in the semiclassical description. So, and what set is that? What operators do we trust in the semiclassical description? And I claim that there's evidence that it's the so-called computationally simple operators, right? So the operators that you don't trust in semiclassical gravity seem to be complicated, like take an exponential amount of time to act, for example. Okay, and so with that as motivation, we prove the following theorem. So this is the boxed theorem that I want, like if you take one thing away from this talk, let it be that this boxed thing, which I'm planning to explain, given however much limited time I have after this. But the takeaway here is that we showed that there do exist highly non-isometric codes such that in these codes, all simple operators are reconstructible, and reconstructible in sort of state-specific, state-dependent sense, but not necessarily complex operators. So the simple operators are reconstructible in these codes we found, but not necessarily the complex operators. And we claim that that's perhaps a good model of gravity. So in other words, information accessible with a simple quantum circuit on the logical Hilbert space is preserved and accessible in the physical Hilbert space. But complicated operators on the logical Hilbert space are not generally reconstructible. And hence we should not trust what the logical state suggests about anything high complexity. And let me note that this is actually quite different from usual codes, not just because it's a non-isometry rather than an isometry, but also because usual codes worry about encoding a subspace or a subalgebra. And here we aren't doing that. The set of simple operators don't form an algebra, right? You can multiply many simple operators together and you you could get something complicated, right? So, and before I go on, so can I ask how long do y'all usually go? I guess we started like 5 minutes late, but.
Yeah, and we're not very strict with time, so just tell me how much time do you need?
I'm running a bit behind.
Okay.
In principle, 20 minutes would be ideal, but
20 minutes is fine. No,
okay.
There have been questions. So anyway, if people want to leave, they can leave.
Okay, thanks a lot. Okay, so let me explain this theorem in a little bit more detail. So, so I'll first define gates and then circuits and then code. So defining gates and the circuits will allow me to precisely explain what I mean by a simple operator. And those are going to be the ones that are reconstructible in the codes that I present to you. So a gate set is just going to be a finite set G of unitaries. Let's say unitaries U and SU4. So these are just unitaries that can act on 2 qubits, let's say. So we're imagining that we have a bunch of qubits, like n qubits, and then we can act any 2 qubit unitary, and we're going to assume all-to-all connectivity. And so I might draw a gate like these orange boxes. And so again, like these blue lines represent qubits, and drawing an orange box here means I've acted that gate on those 2 qubits. And this assumption about the particular connectivity and how big our gate set is don't really matter. There's this thing called the Solovay-Kitaev theorem, which says that any one gate set can simulate any other gate set up to polylogarithmic overhead. So like it would increase the number of gates you need by at most a polylogarithmic factor, which won't matter for us because I'm just going to talk about like a polynomial versus exponential. So polylogarithmic won't change what's in what class. And given that definition of gates, we can multiply gates together to make circuits. So, this is the same, acting many gates on many different qubits. And we're going to be interested in non-isometric codes. of course. So like this V that I've already drawn, it takes in say 4 qubits and outputs 2. And we're going to call the number of input qubits N and the number of output qubits M. And just to so you can keep in mind what these are supposed to represent. Remember that so these N qubits are analogous to the interior qubits, which and then these M qubits are analogous to the stretched horizon qubits. So the exterior guys in both cases are not represented here because V is going to act on them trivially. So they're just going to be going along for the ride, as I'll show you in this next diagram. So so what I'll mean by reconstruction, so when I like the whole theorem is about what operators can be reconstructed and what can't be reconstructed by these codes that I'm going to show you. So when I say an operator can be reconstructed, what I mean is the following. I mean that let's say you have a bunch of qubits and they all start in some state omega. And these qubits don't all have to be qubits that will eventually be acted on by V. You could have some extra reference qubits. And those reference qubits are important. They're not just around there for generality. You're supposed to imagine that the exterior Hawking quanta are like playing the role of these guys, where V doesn't act on them non-trivially, right? That makes sense because the exterior guys can be far away. They can be in a separate reference system altogether in the gravity setting, and so they can start out entangled with, say, the interior modes that will eventually have V acted on them, but they themselves are not going to be acted on by this code. So they all start out in some state omega, which maybe is like this highly entangled state, like a bunch of bell pairs between inside and outside the horizon. And we're going to consider unitaries in the semiclassical description. And these unitaries we're going to imagine are composed, they're circuits, so they're composed of many gates. And the gates could be anything. They could be products of many different gates acting on all sorts of different qubits in the interior and the exterior, on both at the same time. So anything. So this is a general unitary acting on the semiclassical input side. And we'll say that this operator can be reconstructed if there exists a U such that if you hadn't acted this operator up here, so it was blank here, you could have ended up with the same state in the output by instead acting some unitary here on the output. And this is non-trivial. This is not always possible. So this circuit here is reconstructible if there exists a U such that the state here and the state here are approximately equal. That's what reconstruction will mean. We'll say that this circuit was reconstructible. Okay, so what's important about short circuits, so circuits that aren't very long, is that there aren't many of them. So here's a lemma that quantifies that. So let G be the number of gates in our gate set, and then the number of circuits, which we'll say is C. So that number of circuits, all of which take this form, has an upper bound. So a circuit, by number of circuits of this form, I mean number of circuits that involve at most K gates. That number has an upper bound that looks like this. And what's important about this upper bound is that it's exponential in K. There's some other things here, like that appear in the exponent, but they all have logs in front of them, and so they're going to be less important. So what's important is that it's exponential in K, the number of gates. And the proof is straightforward. It just says, count how many ways one can apply K gates, each a choice from G options applied to any 2 out of n qubits. And so if you work it out, that's this number, and then you can bound this number by this exponential here. And with this lemma, where we've counted the number of circuits of length k, you can prove the main theorem, which says the following: that there are non-isometric codes that encode all short circuits, or all circuits of sub-exponential length. So that's the following. So we define V as follows. So remember, V is some non-isometric map from n qubits to a smaller number, m qubits. And the one we're going to prove a theorem about is this one, which is basically, it takes your n qubits, it acts a random unitary on them. So the fact that it's a random unitary will appear in the proof. And then in the output, you're going to post-select a lot of them, so n minus m of them, onto the 0 state. And again, post-selection is this thing that mathematically is easy to do. You just act a bra 0. Physically, it would be difficult to implement it in a lab, but we're not trying to do it in a lab, so it's okay. And when you act this bra 0 to post-select, you end up with a state on m qubits, but it won't necessarily be normalized, not even on average. So we need to just scale it by this extra factor that increases its norm on average. So it's normed 1 on average. Okay, so given this non-isometric code, the statement, non-trivial statement, is the following: that you can get good reconstruction, in the sense I said above, of all circuits of length k with high probability. So probability close to 1, depending on the k. So all circuits of length k with this probability, let's say. So it's 1 minus, and then the second term looks complicated, but let's break it down. It just has 2 factors. This first one and the second one. And this first one is familiar from the lemma before. What's important is it's just exponential in k. And then the second factor is something that's just doubly exponentially small in m. And epsilon, that's going to be your reconstruction error. So if epsilon gets really small, then that can kill this term. That can make it close to 1, which would be bad. But you can make it, say, exponentially small in m and still have this be doubly exponentially small in m, if that makes sense. So epsilon can be like, some really small thing. Then as long as beta is like less than 1/2, like, so let's say beta is like 1/10, then this numerator is still, this part I'm circling is still exponentially big in m. So this whole thing is doubly exponentially small in m. Okay, so the point of this is that we can see that if we allowed circuits, so k's exponentially large in m, then this theorem becomes trivial. It doesn't tell us anything. But as long as k is sub-exponential, say polynomial, then this is non-trivial. We find that with high probability, we can have a good reconstruction of all sub-exponential circuits. That's the statement of the main theorem, to say it precisely. And I will very quickly sketch the proof. I won't go into detail unless someone wants to ask me about it later. So you basically just say, first, it has a few parts, the argument. You say, okay, we can prove that the reconstruction error of a single circuit is small on average. So you're averaging over U here. Okay, so you literally just write down the reconstruction error, like straightforwardly, and then you average over U to compute it, and you can say that's small on average. Then you say, okay, I don't care about on average though. I want to know that if I pick the fixed U, a fixed one, would there be a high probability that the reconstruction error of that one circuit would be small? And the answer is yes. So you use so-called concentration of measure arguments to show that the reconstruction error is good with high probability for any fixed u. I'm going to sort of gloss over the intuition behind the concentration of measure arguments, but I'm happy to go back to it. So formally, we're using Levy's lemma. And what you get at the output is you say, okay, the probability of reconstructing any, like if I just fix the u, then that u with high probability will be able to reconstruct a given circuit, any given circuit. So that the probability that it can't reconstruct a given circuit is doubly exponentially small. Okay. And now finally, we want to say, we're not interested in reconstructing just one circuit. We want to reconstruct all circuits of sub-exponential length, or all circuits of length k. And so what's the probability that we can't do that? The probability that you can't do that, let's call it pk. It's bounded from above by the probability that you can't reconstruct a given circuit times the number of circuits you're trying to reconstruct. And then, so P1 we had computed using the concentration to measure machinery that I glossed over. And then the number of k-length circuits we computed in that lemma, was just this thing that's exponential in k. And then you get good. You with all of this, we've shown what we want. We've shown that with high probability, all circuits of sub-exponential length are reconstructible by a random v. So I will quickly say, but I won't dwell on this extra cool fact. So that was the main theorem. And then now, before concluding, I was just going to mention that these V's are actually really nice in other ways. So they're really nice models of gravity, not just because they're non-isometric codes that happen to encode simple operators, but not the complicated ones. It's also the case that if you use them, say in this way, so here we've had some inputs where we're inputting rho, and some inputs where we're inputting some halves of bell pairs, and the other halves are kept, say, outside, like the exterior Hawking partners. In this case, this models an evaporating black hole where the R qubits outside follow the page curve. So this is a toy model of an evaporating black hole where we have both sides, the two descriptions that I mentioned at the beginning. So the input here, that looks like the state of the semiclassical description, and then the output looks like the state of the manifestly unitary description. This model captures that. So it seems to model gravity at the level of those pictures, has the page curve, the information actually does get out when it should get out, etc. Happy to talk more about that. And you argue this basically just from doing unitary integrals, like in random tensor networks. But to recap, we have demonstrated a new kind of code. So this was the main theorem. We demonstrated a new kind of code in which the encoding map is non-isometric and all simple unitaries are reconstructible, but general unitaries are not if they have arbitrary complexity. And so, and moreover, these codes can nicely model desirable features. Excuse me. These codes can nicely model desirable features of black holes, like the page curve. And one interesting feature is that simple observables in the logical description are physically meaningful, and high complexity observables are not necessarily meaningful. So you can't trust their expectation value in the logical state. So that was, those were the hard results that we showed at the end. And then now allow me to connect this back to the motivation that we started with, that was talking about black holes, and speculate. So given these hard results, the speculation that I would give is that this framework offers insight into the relationship between semiclassical gravity and its UV completion, and that this framework supports the idea that semiclassical gravity is a novel kind of effective theory defined by non-isometric code that preserves just the simple information. So, instead of just having an effective theory whose regime of validity is low energies or low energy densities, this is it. Maybe we should think of semiclassical gravity as an effective theory where one regime of validity is computational complexity, and perhaps the framework with which to do that is with these codes. And so these codes allow for the possibility that semiclassical gravity is an effective description of simple observables. And that's what I have for you. Thank you.
Great. Thanks a lot, Chris, for the very interesting talk. So are there any more questions? Yeah, I was wondering, you mentioned briefly that this reconstruction would be state dependent.
Yes.
Could you comment a bit on this?
Yes. So it's, if I go back to this definition of reconstruction, yeah. So what I mean specifically is that in these pictures where I defined reconstruction, this U here is allowed to depend on this omega. That's what I mean. Yeah. So
but does it have to?
In general, it will. In general, it will. Yeah, in general, it will. Because the basic reason that you should expect that it can't be regular state independent error correction. So let's call the regular error correction state independent error correction. It can't be like that because it's not isometric. And like you can show that if you have a good state independent code, so if you can do good reconstruction of all operators in a state independent way, you have an isometry. That's like a theorem you can prove. We've proven it. So like the intuition is that, maybe I can write it here. Like if the air, yeah, if you have, maybe this equation makes sense. Like, let's say you have this formula holding for all, like, so U tilde just depends on U. It doesn't at all depend on psi. And then this is, and like, so this is like the statement of regular state independent error correction. Then if V is not an isometry, then this can't be true for all psi, because I can pick a psi such that U maps psi into the kernel. So if V is not an isometry, then it has a kernel. Okay, and then this term is 0. Because yeah, V will annihilate U psi by construction. But this term can't be, will have norm 1 because U tilde has to be a unitary. That was part of the reconstruction conditions. And so this will say like sorry, this shouldn't be a 1. Yeah. This will say like the norm of this less than epsilon, which is false.
But usually state dependence is invoked because of the firewall paradox. Like, so is this related to that, or?
That's a very interesting question, which we're thinking about in detail now. My understanding is it's different. So one way in which it's different is that from this point of view, state independence is, state dependence, like is highly non-unique. There's many different U's that will do the same job for any given state. And I think in the firewall paradox setting, there's a much smaller set of U's that are allowed to do the job, and that's important for the argument. I could be wrong about that one. Another difference is that in those settings, once you have an equilibrium state, there's some subtleties here actually that we're just now working out, but that's a very good question. I think it's different. But there are some similarities. Let me leave it at that for now.
Yeah.
can I just confirm on the answer to previous question? So by state dependence of U, do you mean it's dependence on the qubits not acted by V or something else?
Yeah, it's allowed to depend on this entire omega. So exactly. All of these. The qubits that will be acted on by V and otherwise, the ones that they're entangled with.
Thanks.
Yeah. I think Emil has a hand raised.
Yeah, exactly. I wanted to say it. So please go ahead, Emil.
Yeah, so if we go back up a little bit where you're talking about the Hawking process.
Yes. How about to here, would that work? Or further?
Well, yeah, that's probably good enough. Well, so, or maybe it's, I don't know, maybe about slide 18 or so.
Slide 18. Here.
Yeah, yeah. Well, so yes, so in the Hawking process, the radiated quanta are completely unrelated to the state of the black hole.
Yeah.
So, I mean, that's the essence of the Hawking paradox.
Right. Right.
Right, because the radiated qubits carry no information out of the black hole at any time, before or after the page time. So what is it in your scenario that is replacing the entanglement of the radiated qubits with, arbitrary interior partners with actual radiation from the black hole?
With the information, basically.
The actual information that is residing in the black hole.
That's a great question. I thought you might ask this, Emil. Yeah, so that's a great question. So the answer is that the magic is happening with this post-selection here. So maybe I can draw a picture. So if I imagine the input to this code, like there's these bell pairs here, like these are the Hawking partners.
Yeah.
So over here, right, I might draw the same thing. So clearly on this like input side, if I asked about the state here inside this red circle I'm drawing, clearly the state is just entanglement between these guys, which are in the interior, and then these guys, which are in the exterior. But on the output side, the post-selection, the post-selection changes everything. It basically implements quantum teleportation, and the information is teleported out to here, to the outside guys.
But there's no explicit coupling here. So in what sense is teleportation?
Yeah, so, sorry, you said what? There's no
like explicit coupling, right?
Yeah, so in teleportation, all you need is you need to start with some bell pairs or a bell pair in the usual thing. And then you do some then Alice, does a measurement, a bell basis measurement of her side. That measurement is being replaced here by this post selection. And then in usual teleportation, she classically communicates the outcome of her measurement. Here, that's replaced by the fact that we have post-selected instead of measured. So it's like Bob just knows that the state that it's zero. And so that's how the information gets piped out to the radiation. In the holographic map, the information just completely changes places after implementing the map because of this quantum teleportation effect.
Is this related to the final state proposal?
That's a great question. So that's another thing that we're currently in the process of working out the similarities and differences between. So the math, in a lot of ways, is identical. The interpretation, in a lot of ways, seems different, but maybe from some perspective is the same. So I say it's different because in the final state proposal, the post-selection is happening because of some funny quantum gravity dynamics. Like the post-selection is happening, say, like at the singularity. It's all something that happens in the bulk. Here, the post-selection is happening not in the semiclassical physics and not in the manifestly unitary physics. It's happening in the map between the two.
I guess I still don't understand then, because there's some list of qubits coming out in some particular states. So are those qubits coming out in particular order and particular states going to be the same in the semiclassical description and in the microscopic description?
Yeah, so good. So the outside qubits, right? They like you could number them like 1, 2, 3, etc. And then that numbering would have a canonical number, like isomorphism numbering on the
right. So I guess
yeah,
I don't understand. I guess I'm not understanding how a set of random qubits, which is the output of the Hawking process, can ever be equal to a very definite set of qubits, which is the internal state of the black hole.
So
unless at some point the state of the qubits in the Hawking process is being changed by some interaction of some sort.
good. So excuse me. It's so I guess it seems like part of your question there's this subtlety with the fact that the qubits we're talking about are like excitations in some field, and whether or not the field is excited at all seems to change between the two descriptions. That seems to be
where's the information about the interior? I mean, it seems like you're wanting to take what is essentially a random process which generates a set of random qubits and replace it by a definite set of qubits corresponding to the interior state of the black hole. And so I'm still confused about how those two can be compatible.
Okay, so yeah, I think I understand your point. So in this model, the random versus definite is modeled by the states in the input is, if I just look at the outside guys, they're in some maximally mixed state here, like because each one is maximally entangled with an input guy. So this is the randomness. Whereas in the output, they're now in some more definite state because like they contain some information about the interior, and that's the definiteness. And the way that this map has changed us from this complete randomness to the not complete randomness has everything to do with the subtleties of this post-selection.
So is it a fair way of saying that you say, let's take all random states that are generated by the Hawking process and post-select on those states which correspond to the black hole interior in the exact description? So I just take the random Hawking process and I say, let me consider only the particular ones that correspond to what would have happened if the black hole had evaporated unitarily.
No, I don't think that. No, yeah, I don't, because that post-selection involves post-selection. As I understand what you described, it involves post-selection globally, even on the outside guys. Whereas here, I'm just doing post-selection in the map from the semiclassical description of the interior. So just on the interior degrees of freedom to the state of the stretched horizon.
But is that all that different because of the maximal entanglement of the Hawking pairs?
That's a good question. I would have to think about it. Yeah, you pose an interesting way of thinking about it. I would want to process it before I was confident about whether or not that was an equivalent way of thinking about it.
Okay.
Because I would say definitely what's happening is we're post-selecting onto a particular state of some degrees of freedom. And it's like this zero state. It seems surprising to me to say that that's like post-selecting onto this like subspace in which the Hawking process randomly decided to be unitary. But maybe that is an equivalent way. Yeah, thanks. I have to think about it.
Okay, thanks.
And yeah, so another thing is, so when you say that you want to view gravity as a kind of effective theory of simple operators, isn't it a bit similar to this idea that gravity is an average? Like, is there a relation with this, or?
That's a good question. So I think that, so the statement I made does not require or imply the understanding of gravity as an average. Because, for example, in this model, we didn't, like, we used an average in our proof, but in the end, we ended up with a code that just picked a particular fixed u. So our code doesn't have an average. Whether or not they're consistent, like whether maybe you can think of a model in which there is an average and you're only encoding the simple operators. Maybe that's true. For my money, I feel like the connection is that, yeah, maybe like getting some observables right. Yeah, probably like maybe the right way of thinking about the relationship between the physical and the semiclassical is this error correction one. And then maybe you can get a lot of the observables right by doing this averaging. But I don't see an obvious necessary connection either way.
Okay. I think Deepak has raised his hand.
Yeah, hi. So recently there was a paper by Kotler and Strominger, right?
Yes.
I'm sure you must have seen that.
Yes.
So the idea there is, if I understand, that to describe something like an expanding cosmology, for instance, where degrees of freedom are being created, one should describe it in terms of an isometry.
Yeah.
Right. So an isometric evolution. So conversely, let's say that one wanted to talk about a big crunch kind of process. Right. So, I mean, from that perspective, that would be a non-isometry.
Yeah, I think that would be the logical place to start.
Yeah. Okay.
Yeah, I think that's a good point. Like, they made some interesting claims in that paper, and it does seem like, yeah, you can just turn it around and then see what the implications are for the big crunch, and you would then want to deal with the non-isometry, and perhaps the technology here can explain some weird features that you would get there. That's an interesting point.
Okay, thanks.
Yeah, thank you.
I think Akhil.
Hi. So in this manifestly unitary way of looking at it, do we assume the factorization of the black hole and the exterior?
Yes. So I was assuming that the stretched horizon could be thought of as its own independent quantum object with its own Hilbert space, separate from the radiation Hilbert space. Yes, I was assuming that, at least in the model that I was making, to be analogous to that.
Okay, and then we just overlook the issues with that supposition, right? Is at the moment, or?
Yeah, so I guess the issues that you're referencing are the ones that are very sharp in the semiclassical description, where like the entire interior and the exterior don't clearly, it's not a tensor product. So yeah, in the semiclassical description, it's the one that, like, yeah, as I mentioned before, we do overlook that. In the manifestly unitary description, we're overlooking that at the level of this model, at least. And we're still finding these, right? So I think that's reasonable, because to the extent that you can, for example, I could have said all these same words about, say, instead of stretched horizon plus radiation, I could have said it like, about like an SYK system and then some reservoir that it's coupled to, if that makes sense. So, and then I would have still had, if it's clear what I'm drawing. So here I'm drawing like an SYK system where this vertical line is like its time direction, and like this radiation is some radiation that exists in some bath that was coupled to it, and the SYK system, let's say, was dual to a black hole that was radiating that output this radiation. I could have said all the same words that I said here about this system, and made my non-trivial claims about that. And so yeah, these subtleties that you mentioned are, I think, important. I don't think that they would change, like if we treated them correctly, would change the story, because the story would be analogous to this one. I would still have non-trivial claims there.
Okay, and one more confusion I have is like your proposal had necessarily had these qubits which are not acted on by the non-isometry, and which
yes.
can be directly acted on by the U later, right? So could you
Yes.
say a bit more about what characterizes such qubits? I didn't really understand. How do you figure out what are the qubits really not acted on by the non-isometry?
Yeah, so I was allowing there to be some qubits not acted on by the non-isometry, essentially for generality. But in the case of the evaporating black hole, I'm imagining those to be like the exterior Hawking quanta. If you like, I'm imagining, I'll go back up to this SYK picture. I'm imagining like, if I draw SYK's dual or something. So I'm imagining that the map between the gravity description, or maybe I'll write the JT description and the SYK description, that map is V, and that map doesn't act directly on the reservoir degrees of freedom. So that's like the idea behind the fact that there can be in these processes some degrees of freedom that we don't want to imagine V is acting on non-trivially.
So essentially, the V doesn't act on any Hawking radiation. Like by Hawking radiation, if I mean just the
outside
stuff radiated out. Okay.
Yes. Yes.
I'm just confused because like once you start in like, how do you make that distinction once you have interactions and so on? Because like, what's radiated out, what's really like falling in.
Yeah, I mean that could, in gravity, that could be messy. I was going to this idealized setting where we can make a toy model, and the idea was that like in this idealized setting, thanks Deepak. In this idealized setting, we can make these statements, and this idealized setting has some gravity analogs like this one here, where you can say bring the radiation really far away into a non-gravitational bath, and because it's non-gravitational, we imagine that it actually isn't acted on by a holographic map. So the philosophy here is like where there's gravity, there's a holographic map. Where there's not gravity, there's not a holographic map. And so in real life, like in this picture that I've drawn, the radiation, like this, everything here is gravitating. But you might imagine that when this radiation gets really far away, like close to Scri plus, that it's closer and closer to being well approximated by non-gravitational physics. And to that, in that sense, this toy model was modeling that limit.
No, I didn't mean the gravitational effects. I meant like even the Hawking radiation and say some positive normal modes of some scalar, some probe kind of things which are not back reacting. But even then, once you have interactions, they would interact, right? And then I'm trying to understand the.
Yeah. So it sounds like you're pointing out like if I have a setting like this, and maybe there's a Hamiltonian governing the dynamics of these qubits that that couples them or something. Yeah.
Mhm.
And that could happen, and I might try and deal with that in multiple ways. And one way I could try and deal with that is by imagining that all of those interactions I could model as like one of these gates, or some of these gates coupling the two, and
Right. So the I should think of K as some perturbation theory order. Is that all right?
At least you can include these perturbative interactions in among these circuits. Yeah, as part of these circuits.
Okay, thanks.
Yeah. Thanks for the question.
I think some data has raised its hand.
Yeah, so you're saying that there's a non-symmetry between the degrees of freedom in the interior when you kind of apply some operator and convert them to degrees of freedom on the stretched horizon. Is that right?
Yes.
So in general, in principle, I would suppose that once you have a certain set of degrees of freedom in the interior, you should be able to have a unique map to the degrees of freedom of the stretched horizon. I mean, there shouldn't be any error in that. Isn't that correct?
Okay. Yeah. I see what you're getting. Yep.
So in principle, there shouldn't be any symmetry loss. I mean, there shouldn't be any non-symmetry at all, because there should be a unique one-to-one map between the two sets of degrees of freedom, if I'm not wrong.
Okay. Yeah, I think that I just slightly, I would slightly amend that by saying that the semiclassical description is just an effective one. That's my point of view here. So as just an effective description, it might not get all of the UV non-perturbative physics right. So it doesn't know everything about the UV physics. So in other words, I actually would be okay with there being some error in the map from the semiclassical to the semiclassical interior to the stretched horizon state, and that error is not because the stretched horizon state has lost information or doesn't know something. It's that the semiclassical state doesn't know something.
Okay, so by the semiclassical state, you mean just the area of the horizon, is that right?
No, by the semiclassical state of the interior, I meant, like if I scroll back up.
By the stretched horizon, by
semiclassical, I mean like this stuff. Yeah. So I mean not the stretched horizon. Yeah, by the semiclassical, I mean like the description of the interior of a black hole that like Stephen Hawking would have given.
Is there a semiclassical description for the interior? What sort of semiclassical description exists? I mean, I'm not aware of.
I just mean like take classical GR and the way it imagines the interior of a black hole, and then quantum fields on top of that background. So it's not a complete description of a black hole, but it's the way we would describe the black hole in semiclassical gravity.
But then what you're describing is just the opposite way around of what you were describing before, because you were saying that the interior degrees of freedom were more in number than the degrees of freedom on the stretched horizon. Now you are saying that the interior degrees of freedom are described as some semiclassical theory, which has less information than that of the stretched horizon. Isn't that correct?
Yes. The semiclassical description, more degrees of freedom, but not all of the information, perhaps. Yeah, that's the subtle part. So in this model, it's not clear what information the stretched horizon has that the semiclassical description doesn't have. I'm just saying that in real life, in gravity, I wouldn't be surprised. Like in this model, there are errors in the translation from the semiclassical description to this stretched horizon description, but I don't interpret those errors as a failing of the stretched horizon description. I interpret it as a failing of the semiclassical description.
Okay.
Thanks for the questions.
And so here in the picture, it seems that you look at the black hole you get from collapse. Like, is this important, or can you also consider typical states, for example, in ADS?
Okay. Yeah, yeah, it doesn't have to be from collapse. That was just a convenient thing to talk about because I wanted to talk about evaporating black holes. Yeah, you could also imagine starting from like these SYK, like eternal black holes. Yeah.
But I have another question. When you are saying that you're error correcting, initially you had this picture where you had these small b's and then you had the large b. The large b was the error corrected code, right?
Good. Yeah.
Yeah. So here now you have, in place of the large b, you have the stretched horizon, whereas in place of the small b's, you have the interior
Exactly.
degrees.
Exactly. Yeah.
So I would suppose that the degrees of freedom on the stretched horizon, since they're error corrected, they should be less than they are the error corrected degrees of freedom, not the interior of the black hole, as you were just saying.
Yeah, good. So this is part of the weird new terminology. So yeah, we're right. So usually when people talk about quantum error correction, they have these isometries for the reasons you're pointing out, because you want the physical Hilbert space to be more resilient to errors. So here with a non-isometry, it sort of flips around, where the physical Hilbert space isn't necessarily more resilient to errors here. It's still error correction in the sense that you have these non-trivial reconstruction statements. Like you can say things like, oh, after the page time, the radiation can reconstruct operators in the interior. And I didn't get to cover that in great detail. But so you can still talk about reconstruction in these non-isometric codes. But yeah, it is a little counterintuitive for the reason you're saying, that you can have a code in which the input has more degrees of freedom, and somehow it's packing all of that information into a smaller number. So it seems like the smaller number is not more protected from errors. And to some extent that's true, but it still allows some non-trivial reconstruction statements.
Yeah, so you're essentially saying that even if the stretched horizon has lesser number of degrees of freedom, it has more information. That is what you're saying.
Yeah, in this model, I wouldn't necessarily say, it can have more information. Yeah, exactly. I would agree with that. Yes.
Okay.
Like some of the information, just to be very clear. So some of the information about the semiclassical state is lost in the translation, but I want to give it the interpretation of being unphysical in the first place. So there was some information in the semiclassical description that was sort of unphysical, extraneous, and just sort of there to help, as part of the semiclassical description, but it wasn't physical because it gets lost in the translation to the true microscopic description.
But I would be hard put to imagine some operator that does that. I mean, it takes some scrambled state and converts into some meaningful state. I mean, what sort of operator does that?
Yeah. So these V's that we found, right, that basically act to Haar random unitary and then post-select, they take in this, I'll scroll down. So they take in this state that looks like the semiclassical state, right? Like it has a bunch of entanglement between the inside and the outside. And then, yes, this unitary does scramble everything up. And then the post-selection does delete some of the information. And the essence of these codes is that we're showing it only deletes sort of the information that would have been very complicated to access in the input. So it keeps all of this, the simple information. And the idea is that you should think that it's only the semiclassical description was trustworthy for the simple information, but the complicated information that was there, it was not trustworthy. So it doesn't matter that it's deleted as it goes to the physical description. That was sort of extraneous information that was part of the semiclassical description and not physically there.
And can you describe this entire process in terms of, say, creation and annihilation operators?
We haven't done that. That would be interesting. You'd have to. That would be interesting. You have to somehow use annihilation operators to create this post-selection. Seems difficult. Yeah.
So what is the basis of your analysis? I mean, if you don't have a concrete kind of description of how the process is taking place, what is the basis of your analysis? What are you basing it on?
Yeah, so the basis is these theorems we started with. So the idea is we're noticing that the quantum extremal surface formula can be applied to compute the page curve in black holes. And we have these theorems that say where there's a quantum extremal surface formula, there is quantum error correction. But then by thinking about that, you get all these puzzles. How can there be a quantum error correcting code at play here? It would have to be non-isometric. And so what we're proving, the result that I am telling you in this talk, is that actually that's not a puzzle. We figured out there are codes that do have all the right properties so maybe there is such a code, slightly more complicated because it applies in quantum field theory, but maybe there is such a code that works like this in gravity.
Okay.
And so in gravity, like, do you have an idea of what would explain this post-selection? Or is it just a toy model of such a non-isometric code?
Good. So, right. So I imagine that in gravity, yeah, it's just part of the map between the semiclassical description and the physical description.
So it would depend on UV physics, like.
Yeah, it would depend on both the UV physics, the semiclassical physics, and whatever the relationship is between them.
I see.
Yeah.
Okay. And yeah, just another question. Yes, so I think similar ideas have been proposed some time ago by like Verlinde and Papadimos-Bajou, but in the context of the firewall paradox. But I think your story is a bit orthogonal. Like, is that correct to think of it that way?
My story is a bit what? What was this? What was the
It's
word?
a bit orthogonal. So
a bit orthogonal.
Is that correct?
Yeah.
Or?
Yeah. So yeah, right. So what's new here is that we are we're not the first to talk about black holes and quantum error correcting codes. What we're proposing is that it makes sense to think of them as non-isometric codes. And our evidence is that there exist non-isometric codes with all of the right properties.
I see.
Yeah.
Okay, thanks.
Yeah, thanks for the questions.
So are there any more questions for Chris? I think we already 1 hour after. Okay, so if there's no more question, so let's all thank Chris again for the great talk and discussion. So thanks a lot.
Thank you all very much.
Yeah.
This is fun.
Yeah. Let me end the meeting now. Bye.